Hello and welcome to the third episode of Spacetime Fika, a podcast about physics and astronomy. In this episode, I discuss how we make sense of the universe with the help of astronomical images. My guest is Luis Calzada, who is a data visualization artist at the European Southern Observatory, also known as ESO. This organization builds and runs some of the most powerful telescopes in the world, and it's Luis' job to make sure that the data collected by these telescopes is presented in a visually appealing and educational way to the general public. Chances are pretty high that if you have watched space documentaries or followed astronomical outreach events, you might have seen some of Luis' images or videos. I met Luis while I was working at the communications department at ESO, and we sat down one afternoon to talk about the meaning of astronomical images, how they are produced, which role they play in outreach, and what it is like to first do an artistic illustration, in this case of the surface of Pluto, and then to actually be able to compare that illustration with real scientific data as it arrives several years later. Links to the images that we discuss can be found in the episode description, and I hope that you enjoy our discussion. Okay, Luis Calzada, welcome.
Thank you. Pleasure. Thanks for having me here.
You're welcome. And we're going to talk about astronomical images that you're involved in making here at the European Southern Observatory. But let's start to talk about a little bit about you and your background. So how did you get started with astronomy and visualizations?
Well, astronomy, I think since a kid, I wanted to do some science. I was very into science. And there's this anecdote I always like to tell people. I was a kid. I was with my parents doing groceries at the supermarket, and I saw the cover of the Carl Sagan's Contact, and I didn't know him at the time. I was 14, maybe 15, and but I really liked the cover of the. I think it was a Portuguese edition at this crescent image of the Earth, but it was an illustration, not a real image. And that got my attention, and I asked my parents to buy the book. And then of course, after that book, it was a novel. But after the book, I was really captivated by the topic of space and astronomy. And then I started buying other books from Carl Sagan. And and that was pretty much how I decided that I wanted to study astronomy. And but it's funny because now I'm doing this astronomy visualization, and and it's funny to think that it was the image on a cover of a book that got my attention and got me into astronomy, and now got me, doing what I've been doing for the past almost 20 years or something like that.
So it's Carl Sagan is the reason that we're sitting here talking today.
Yeah, literally.
That's very funny. And then, so you studied astronomy at the university, right?
Yeah.
In
Porto. In Porto. Yeah. At the time, it was the only place where you could study astronomy in Portugal. So it was the only astronomy degree. So pretty much every Portuguese astronomer you meet from around my age, my generation, we all come from the same place, and people always find it funny. We all know each other, but there's a reason we all studied in Porto. Yes.
Right. And I noticed it's here also at the European Southern Observatory that there are many people from Portugal. And Porto in particular.
That's the reason.
Yeah. Funny. Okay. And then you started working eventually here at, we call it ESO, but let's say the European Southern Observatory. So before going into that step, how did you do the transition from pure astronomy and also doing the visualizations?
So while I was doing my studies, I started working in a planetarium in Porto. Well, close to Porto, a small town called Espinho. There's a lovely science center planetarium. And I was just working there. Many of us did while studying astronomy. It was a cool place to work and to get some money while doing my studies. And there we were working on some planetarium shows, very typical things. And then here and there we would need, it would be nice to have an image of this or that. And this was the early 2000s. And if there was nothing we could use, I started thinking maybe I could do it myself. And some friend showed me some 3D programs at the time. I think I started with Bryce. Maybe some people still remember that. It was really quite unique program. And I just started fiddling with it just for fun for this planetarium shows. When I started getting the hang of it and the taste for it, and then very fast I started using Cinema 4D. It was another software that I still use to this day after 20 years. But it was mostly just for fun. It was not fundamental, but I started experimenting with it and I started enjoying it. So I started learning while doing my astronomy degree, and became serious about it to the point that, well, that's what I do now for a living.
So exactly what was it that you got you hooked in when you used this program the first time?
I mean, I always enjoyed the technical aspects. So the nerdiness, let's say, of this software, the fact that you could simulate, light shining, the way atmospheres mess with light, and you could see this already in these softwares from the time. And that was, I have to say, it was actually the technical aspects that got me into it so much. So even the softwares themselves, the way they rendered, the physical rendering, the ray tracing, the physics of it, I was captivated by it. So I got into it because I liked the technicalities of these 3D programs. And but then, of course, very fast I started, enjoying the fact that I could actually create, stuff that were potentially real that we couldn't see, but I could imagine them. So I think that was pretty much what got me into it so fast, was the blend between the science, and the art, plus the technical aspect. The almost the engineering of this software was also very, very interesting for me. So I think it was the mix of all these elements: the science, the technology, and the art, because that's something about me as well. On a personal level, I like to do a lot of stuff which is artistic, photography, music. So I always had these two faces: the scientist and the artist. So I think I started finding precisely in this world of astronomy visualization or science visualization, the perfect blend between all these things I like a lot about.
Yeah, it's really cool. And we're going to look at some concrete examples how you use these programs also to create these images later on. So, but okay, so you were in Portugal, Porto Planetarium, studying astronomy, learning this program. And how did you end up in Germany, outside of Munich?
I mean, two reasons. The biggest one, of course, it's ESO. ESO is one of the biggest places in the world, in Europe, where you can do astronomy-related stuff. So I think a lot of the people who studied astronomy or are involved in astronomy, somehow their career goes through this place. And a colleague of mine that was working with me at the time, he moved to Germany to do his PhD. So he finished his studies. He was working with me at the planetarium. He moved to Germany and he was doing his PhD. And then he saw somehow this job advertised at ESO, and he said, "Oh, you should maybe try, because you've been doing this astronomy visualization stuff." And I decided to try, but I didn't even imagine I would get the job. So only when I got it, I was like, "Oh, looks like I have to go to Germany now." And it was not at all in my plans, and this was in 2006, and I applied for the job. I got the job, and that's it.
And that's it. No.
The rest is history, like they say.
So did you send a portfolio when you applied for the job?
Yes, as well. Yeah, and then they brought me here for an interview. I mean, at the time there was some other tasks, because the ESO was doing. I mean, the communication group was a little bit different at the time. There was a big focus on exhibitions, so there was some other things involved. I think the heavier focus on the astronomy visualizations came a little bit later. But so in the beginning there was also some other things involving exhibitions and that kind of stuff. But yeah, so it was kind of a surprise to me that in a few months my life changed and I moved here to Germany. So, but it's been great. I mean, being part of the team here.
Cool. So let's jump to today. And what do you actually do at the European Southern Observatory?
So, I mean, the group does quite a few things. We do all kinds of communication for ESO, the website, publications like annual report, messenger. So we do quite a few things, print stuff, communication with community. We also have a planetarium. But me, I focus obviously in on the visual side, producing visuals for the press releases mostly. So infographics, illustrations, videos, animations, all that kind of stuff. I do a few more things as well. I mean, if there's a bit of photography that needs to be done, I also like doing that. So everything to help the communication group. So we're a big team. There's a few of us doing what I do specifically. There's two of us, mainly me and Martin Kornmesser. He also, people who are interested in the topic, and if they're listening to this, they probably know as well the name of Martin Kornmesser. His images are also everywhere. But yes, I mostly focus on the visual stuff, illustrations, animations, infographics, all that kind of stuff.
So how many, on average, like how many images and videos per week do you produce?
Well, it's hard to say. Of course, naturally, one of the biggest thing is the press releases. So we have them, we have 30, 40, 50 per year, let's say. Yes, or maybe less, maybe more. So some of them, obviously, we have images from the telescopes. That's probably something you're interested about, and we're going to talk a little bit about the difference between the images that come from the telescopes. But many times we don't have those images, so we produce illustrations. Of course, even if you have an image, sometimes you need an infographic to kind of make some of the scientific phenomena in that press release. We need to do some infographics, maybe some videos as well. So it's hard to put a number, but yeah, I would say maybe 20, 30, 40 per year. I don't know. It's hard to say. It's really hard to say.
Okay, so but quite a lot. Okay, so let's dive a little bit into this question of producing scientific images, producing artistic illustrations, the differences between them. And I thought we could just start again with the European Southern Observatory, the actual telescopes, just for the listener who maybe doesn't know exactly what ESO does on that front. So there are telescopes in Chile, right?
Exactly.
And what happens in Chile?
So I think, okay, so very quickly, the history of ESO and the name, the European Southern Observatory, it's funny. But the reason was that for many, many decades, most of the astronomy was done in the northern hemisphere because that's where the rich countries were. That's where the telescopes were built. And then in the 40s, 50s, 60s, astronomers realized, well, we need to know a little bit more about the southern sky. That's also where the center of the Milky Way most of the time is. So that's why ESO came to be. So a few countries got together. Let's build some big telescopes, bigger than what the individual countries could do, and build them in somewhere in the southern hemisphere to observe the southern sky. So that's why Chile was chosen. The telescopes are built in one of the driest places in the world, where you get many days free of rain. So you get clear skies. And of course, we build them as well in the high places where you get even clearer atmosphere, thin. So that's how ESO came to be, and the telescopes are built. So nowadays, the first observatory was La Silla in the 60s. It still runs a few telescopes there. Then in the 90s, the VLT came to be. So VLT is a very large telescope. ESO is famous for having funny names for the telescopes. The VLT, the Very Large Telescope. So that's 4 8-meter telescopes that can work together using interferometry, plus 4 smaller telescopes, which we call auxiliary telescopes. And now ESO is currently building the ELT, the Extremely Large Telescope. And besides that, ESO is also partner of ALMA, which is the Atacama Large Millimeter Array, which is a collection of radio antennas built with the Americans and Asia as well. So it's a bigger consortium that ESO is part of.
Yeah. So, and it's some of the best telescopes in the world in terms of resolution and
exactly. Yeah. So and the ELT specifically is going to be the biggest telescope in the world, and it's set to start operation in the next 4, 5, 6 years. Let's see how it goes. It depends on how optimistic you are. But and yes, of course, the VLT is one of the biggest, best, most productive telescopes in the world. Ground-based, of course. Yeah.
Ground-based, exactly. Yeah. So, okay, so this is very fascinating. So we have some of the best telescopes in the world. We get data from them from the universe, and somehow we have to use that data then to understand the universe and also visualize the universe and understand what is going on. So let's talk first about the difference between a scientific image and an artistic illustration. So because when the general public sees images of space, it's not always certain for the general public, like, what am I actually seeing here?
Well, yeah, so I think that's a good question, because it's I think people imagine telescopes and astronomers as still as Newton and Galileo, right? Just looking through a very small, lens and a magnifying glass, let's say, almost. But modern telescopes are not like that. I mean, the principles are, you still need a lens or a mirror. Modern telescopes use mirrors, not refracting lenses. But you still need, so the principle is the same. You collect light. So the bigger the telescope, more light you have, and more information you collect. But you don't sit and look through the eyepiece anymore. You have cameras, very advanced cameras. And more than cameras, I mean, these are instruments. They capture the light and do all kinds of interesting and complicated thing with the light. So basically, these telescopes, these machines are collecting light information, and then it has to put together in a certain way. So astronomers, what they do is they analyze this light in many different ways. You can split the light in the different colors, which we call the spectrum. They analyze black lines in this spectrum, which are caused by the chemical elements either emitting on those objects or absorbing in between the objects and us. So there's all kinds of different things that we can do with our light. So and somehow for the astronomers, what matters is the information, so the numbers that they get through the telescopes, let's say. It's not so much, of course, naturally, also the images can be important because you can do a lot of things by looking. But yes, you could nowadays with computers, with software, with algorithms, you can analyze all the data. So the images are made sometimes, I don't want to say as an afterthought. I think maybe it's a little bit unfair. But for the public, we produce these very beautiful images that people are so used to see when they think about astronomy. They think about these very beautiful, colorful images. But these have to be put together with the information we get from the telescope. So it's a complicated process. It's not as you don't press a button on the telescope and then you get this very beautiful, colorful image of a galaxy or a nebula. Depends which filters you were using, which frequencies you were observing. Because you get X-rays, infrared, ultraviolet, all kinds of different light from the objects depending on how you look at them, and they can look very different depending on how you're looking at them. So I know it's a very long answer to your question, but because it is indeed a very complicated process. Not complicated, it's more like the same way a doctor has all this kind of X-rays, MRIs, all these different kind of instruments to look into your body. The astronomers have all these kind of different cameras and instruments mounted on the telescopes that can do all kinds of things with the light we get from the universe.
Yeah, that's a very good analogy. And I like to think about it that, as you mentioned, Galileo and Newton, it's an astronomer that actually looks with their eye. So the eye is the instrument registering the light. And then later on we had the photographic plates, and then you actually got an image. But as you say, today it's a very involved process. And what you get at the end of the day that you send around to other astronomers, that's a digital file, right? Like a bunch of zeros and ones at the end of the day.
Exactly. So that's pretty much it. And it's really funny. And it's very, very interesting because when you try to explain this to the layperson, you start thinking inside your head, inside my head, I do this. There's actually a lot of interesting things to explain to people. Where are these images come from? Besides the, whatever physical processes are happening in the object far, far away in the universe, the process of us creating these images is in itself very complicated, but very interesting, very, very fascinating as well. Because again, what region of the spectrum are you looking? Are you looking in radio? Are you looking in infrared? So all those different things make the object look completely different. And it's sometimes putting together an image of what an object really looks like. I don't mean like a real image, but like a mental image. it's again the same thing. Like if you look at someone, through X-rays, you would think, oh, a person is just a bunch of bones. But you need to look, with other instruments to put the full picture of what the person really looks like, right? So that's quite interesting.
Yeah, exactly. And so talking about mental images, that's the other aspect then, that one thing is to produce scientifically based images based on the data that the telescopes collect. And another one is to create then these artistic illustrations. So what is that?
Well, I think, the answer to that comes in continuation of what I was saying before, is that there's many cases that you cannot even make a proper image of the object because you don't have such a thing as an image. You have data, you have information, you have light, but maybe it's a source point. It's a point source of light. You cannot even reconstruct like a proper image or how we usually think of an image. But we can infer a lot of things about that object with the light that we're getting from the object. Is the light red shifted, blue shifted, because the object is spinning, or is what temperature is the body? We can infer that from black body curve of this emission, for example, or which color should it have? We can look at the spectrum and the chemical composition. So there's a lot of things we can infer from the data, even though it's not a real image. So and that's exactly the kind of stuff I usually do, is to create some artistic visions of what this object might look like, but always trying to use the information we got. Of course, naturally, there's a little bit of imagination, but the main goal, the main challenge is always to produce something which we believe should be kind of close to what this might look like. Not even if it's not to our eyes, but to a camera, which would be placed maybe a little bit closer to the object or with a little bit more sensitivity than what we currently have.
So let's look at a concrete object. This is so fascinating to actually translate this scientific data into artistic visualization. So we're going to talk about an exoplanet called WASP-76b. And there will be links to all of these images that we're going to discuss in connection to the episode. So to begin with, when I see this image here, I see something like atmosphere, there's light coming in from the left, there's clouds, there seems to be some kind of floating lava-like material in the lower part of the image, and then there's this rain falling down, and that rain looks also like it's burning almost. So what is going on in this image?
I think it's funny that you picked this example, because I think it's a really interesting example by many reasons. Because first, I didn't do this one alone. I did it in collaboration with Martin Kornmesser. We work often in collaboration. And it's funny that you mentioned it feels more like a painting, because indeed my background is in astronomy. Martin's background is in art. So he tends to be more like the artist on our duet when we do collaborations, and I'm more the scientist. So I did a lot of the more technical aspects of this image, and then Martin was painting on it. So yeah, that's why he has this painterly look. But we try to represent very physically correct, as we always do, what's going on here. So, and this is like a giant planet that the scientists know is very hot in one side, is very close to the star, and very cold on the other side. So they know that it's a giant planet, gaseous planet. So they will know there would be a very, very sharp edge between the cold and the hot side, and they think that there would be like a big wall, like we represented here. Moreover, they detected that there's iron on the planet, and they know from the temperature of this planet that this iron should be in the gas in the gas form. But as it goes to the dark side, where it gets colder, it would condensate and rain. So we call this image this planet the iron rain planet, because they think there should be an area where it rains iron. It's really cool.
It sounds amazing. And this was detected with which one of ESO's telescope?
This was with the VLT. Yeah.
Okay.
Yeah. So I think most of the recent discoveries, or the biggest ones, are done with the VLT. Naturally, the LaCie, some of the telescopes are still in operation, obviously. But yes, some of these discoveries have been with the VLT, like this one.
Okay, so the astronomers So, with the help of the Very Large Telescope, they could see that, okay, there is a planet orbiting around another star. It's extremely hot. It has some kind of boundary, probably. And on one side of the planet, it could be raining iron. Now, that's quite something.
Yeah, it feels right. I mean, a lot of this, I mean, the scientists are like this. I mean, and again, this is based on a lot of hypotheses, but that's science, right? I mean, in a few years with more data, maybe they will discover, oh, it was not iron. But for now, with all the data they have, you know, they can say it's iron because they can detect, they could measure the spectrum of the light coming from the planet, and they could infer, they could see the lines, the spectral lines, which we know come from iron. So they know it must be iron. So, and it feels funny, right? We don't see it, but we can detect, for example, the wobble of the star. And we know if there's a wobble, there's ways in which we can detect the wobble by looking at the light of the star and seeing how it becomes red and blue shifted as it moves towards us and goes far away from us. So we can detect it as a planet there. We can detect the light from the planet and do the spectrum and see which elements are there. They know the temperature of the planets, so they know the dark side, which is facing away from the star, will be much colder than the hot side. So yeah, but that's science, right? You create hypotheses with the data that you have, and then yes, we cannot see it, but we can draw an image to kind of represent more or less what we could see potentially. I mean, naturally, this is one of the cases where we think it's pretty fantasious, but all the elements in the image are based on the science. A colder part, a hotter part. We know it's gigantic, so it should be a gaseous planet. We know that there's iron. It should condensate. So if it condensates, there should be rain. You know, all the elements are potentially real with the data we know. So they're in the image.
So what happens then when astronomers do this detection and then they come to you and Martin and they say, hey guys, can you make an image of a planet where it's raining iron?
If you say like that, it sounds funny. No, so of course, I mean, we have a process. People in the team, they select candidates. So they select, or they're contacted by the scientists doing science with the ESO telescopes and say, hey, we have this paper release, we have these results, we're very excited about them. Do you think we can make a press release? Let the press know about this, let the public know about this. And our colleagues judge. Of course, they say, oh yeah, this is exciting. This looks very interesting. Because I mean, the role is that we get this science to the public, because scientists have their way. I mean, they publish their papers go to other scientists, and that's how science is made. But we also want to share this with the press, with the media, and with normal people that are interested about what kind of stuff the astronomers are doing with the telescope, especially because ESO is publicly funded. So we also want people to know where the money is going, right? So, and I think that's quite interesting. Yeah, so our colleagues, they judge the candidates and then they say, oh, this is really interesting. And then when we decide, let's make a press release, what is the story here? What are we trying to tell people? What can we show them? I mean, then do we have images? What do we have? No images. Then let's create something that kind of represents the excitement of the story, because I think that's the idea. Is we don't create images of iron raining in a planet that we don't know if it's there just for the fun of it. The idea is that we want to captivate people, right? Because we know the science is exciting, but we want to show it to people in a way that catches their eye, and that's how it goes. If we want to end up on the cover of a magazine, on the cover of a newspaper, on the top of the New York Times or the Guardian, and you do that by a captivating image. So we know that there's this aspect of the work we do is to kind of like create this eye candy to get the first attention, and then we tell them the story we want to tell.
Yeah. But it's very important, as you said here, that the eye candy has a scientific basis. So when you made this image, for example, of the raining iron onto the surface of this exoplanet, was there like a back and forth between the scientists, and were you changing stuff as you went along making the image?
Of course, yeah. I mean, that's one of the signs of our work, where we are very, very careful, so that we we always, not always directly us, the artists, me and Martin or other colleagues, but the people in the team that coordinate, so that do the bridge between us and the scientists. We all work closely together. We know from the beginning, so what is the story? What are we trying to tell? What do we know about this? And then we do some first iterations, and then we send it to the scientists, and then they say, no rocky surface. This has to be, it's all full. This is a gas planet like Jupiter, so there wouldn't be a surface.
So you had made a rock surface the first time?
Exactly. So there was a first version of this where we had some rocky surface, and the scientists said, no. It's from the size, we know for a fact that it won't be a surface. And that's exactly science. So, they don't see it, but you don't need to see it to know, because if you can detect the mass, you can detect the mass from the wobble of the star. So we know how big the planet has to be to create that big a wobble on that star. So we know the mass. And if we know the mass, then we know, we know a lot about planet formation. So we know after a certain mass, the planet will be closer to a gas giants like Jupiter or Saturn. So there won't be a surface, or if there is a nucleus, which is probably too hot to be solid. So that's, we don't see it, but we know. We know with a certain degree of certainty. So when we get all this data, we try to, from the beginning, already create an image like that. But sometimes we don't have enough information. We do a sketch, and then they say, no, please change the color. It should be hotter, should be bluer. No, it should be rocky, should be gaseous. So we always iterate with the scientists until we are all happy with the image, Because indeed, these images, we want them, of course, naturally, eye candy. Maybe we're doing a bit of a disservice to these images, because yes, we want to captivate people, but we also want, some of these images, they end up in Wikipedia, they end up in books. So people will learn from these images. So we want to also convey a vision of how these places or how these objects should look like, as much as we can.
These images are often called artistic illustrations. Is there a risk there that maybe people think that they are fake because they're based on science? Should they be called scientific illustrations? Or
depends. Many people call them artistic impressions. So they're impressions of what this object might look like, but there's art because there's subjective view to a certain extent. So, but some other people call them science visualizations, but you could also say science visualizations are ones which are more like true to the data. Depends. It's very semantic, right? It's really depends on how you wanna call them. But the only fantasy is in the aspects that we don't know about. But even if we don't know about, they are still physically based, right? We're not going to put 3 stars if the system only has 1, right? Just because we think it looks great artistically, we wouldn't do that, because we wouldn't make the star green, because we know there's no such thing as stars which are green, just because we would like to see a star looking green on this image. So that's it. Even if we don't know some things, we know from the science of other places in the universe that you shouldn't have a green star, for example. So the name, depends on how you want to call it, because we know they're not real images. Naturally, it's important that the public knows they're not real images. That's why we call them. We always are very careful to have on the captions of these images that they are subjective, artist-created renderings of what this might look like, and not images straight from the telescopes. That's very important to make that distinction. Yeah.
So that's the science perspective. Looking at it from the artistic perspective, often when you talk with artists, whether it's like musicians, composers, or painters, one often hears that you can get more creative by having more constraints. So being forced to constrain yourself in certain ways when you're painting or when you're composing, only using one instrument or only using a certain set of colors, for example, can unleash creativity. And in this case, you have the science as the constraint in your creative process. Can you talk a bit about that?
I think that's quite interesting. Depends also who you ask. I would think, I'm quite sure if you'd ask Martin Kornmesser, he would say that he's happy when he has less constraints, because I think he can can become a bit more free. I'm actually quite happy when I see the more constraints, because I'm more excited about creating images and visions which are closer to what potentially this object could look like, because I think that's one of the really exciting things. I know we're creating images which are probably most of the time very far away. I mean, naturally you wouldn't have such a view on this iron rain planet, but we know that something similar to this must be happening there. So what I want to say is that for me, it's quite exciting to think that some of the images I create can potentially be very close to what the object really looks like. Of course, naturally, this is just maybe just a matter of personal pride, but it's just funny to think that. So I'm quite happy to know when there's constraints, because that means we know a lot about these objects. We're very close to knowing how it really looks like, and I'm just helping. I'm just giving the final help of maybe this is what it looks like by putting in the missing parts.
Yeah. So we're going to look at an object now where I think it's so funny or fascinating, because you made the artistic illustration before we knew what it actually looked like. And then we got the data and got true scientific images of this object. And you could compare your creation with what the spacecraft called New Horizons saw of the planet, or not planet nowadays, dwarf planet Pluto. So can you tell me what happened here? You made an artistic impression of what the surface of Pluto would look like. When was this, and when did you do this?
It's funny, because we were talking about this beforehand, and we knew we wanted to get to this point, because it's an interesting point. Because most of the things we work on, if we don't have a real image, probably we're like decades away from getting a real image for most of these things. Exoplanets, with the next generation of gigantic telescopes like the ELT and others, we might start getting better images, direct images of extrasolar planets. So we know that when we do most of these images, we're decades away from actually seeing something close to what we're illustrating. But there's a few very small examples, and it's very exciting actually. Pluto was one of them, because up until a few years ago, we had only very bad resolution images of Pluto with the instruments we had. And some years ago, we had some science release about the atmosphere of Pluto that was done with ESO instruments, ESO telescopes. And then we needed to make an illustration about this methane which was frozen on the surface of Pluto. And at the time, it was also a very cool exercise to kind of imagine a little bit how the surface of Pluto would look like, how the sun would look like, from the distance. And this was done very closely with the scientists. It was a very cool process, imagining, the sun, how dim it should look like. It's funny to think that from the distance of Pluto, the sun starts looking more like just like a star than the sun which we used to seeing here from the Earth. That was one of the things. But also imagining how the rugged, rocky surface of Pluto could look like, with some patches of this ice from methane. And then it was really cool a few years ago when finally New Horizons captured some images of Pluto. It was so cool to see how close we were from this. From the reality of the surface of Pluto. Naturally, I have to stop patting my own back, because naturally it's still just a rocky planet with some ice. It's not that we imagined something which was unimaginable, but yes, still it was quite an interesting feeling for the first time. I think this happened to me, that to see one of the illustrations I had made. Actually, now we got some real images of the object, so it's cool to see that.
Yeah, so let's talk a bit more about that. So I have the images here in front of me, and as I said before, we're going to link to all the images so the listener can see them for themselves. But let me try to describe first your image, and you can fill in if I'm missing something. You made an artist impression from 2009, and that was based on observations done with ESO's telescopes. And in this image, I see in the upper part, I see the night sky. To the right, upper right, I see a very, very dim and far away sun that looks very bleak. And then I see the horizon of Pluto. And in the middle left of the image, I also see one of Pluto's moons, Charon. And then on the surface of Pluto, there is, as you described, there's this icy, rocky surface which has kind of textures of some impact craters and some very small mountainous features, and the surface doesn't look like a place where you would buy a house and,
I think property is very cheap there.
Yeah, exactly. And
I think another thing which is very important is this very thin atmosphere, which was one of the core results from this result, science result of this press release, was this thin atmosphere of Pluto that they detected, and some of the components of the atmosphere, and that's something we also see then from New Horizons images. It's a very thin atmosphere, but it is there. I mean, it's a small. Well, we cannot call it a planet.
Nope, that's not allowed.
It's in the rules. We cannot call it a planet. No, but we know it's a small object, so it might hold some atmosphere, but it has to be very thin because it wouldn't be like on Earth, because atmosphere would escape. Yes, and again, the sun. We know from the distance that the sun has to be very dim, very far away, and we know also the size of Charon of Pluto's moon. So those things are easy to kind of represent, right? We have an idea of how it could look like. But yes, the atmosphere, the thin atmosphere, patches of ice that should be present because we know the very low atmosphere, very low temperatures from this distance. I mean, you can imagine it's freezing over there, right? So we had some elements. We know there would be craters because again, if it has a very thin atmosphere, little protection from meteoroids falling, so for sure there would be craters like on Mars and on the Moon.
And then we have the image from 2015, and to be honest, it looks very, very similar to your artistic impression. I think it's amazing.
Yeah.
We also see these small surface irregularities, small mountainous features. We see the icy texture. We see the thin atmosphere. Also the dim light that we have here. So it's very, very similar. It's amazing.
Again, we're not talking about this example as to give me credit. I mean, the credit again is to the science, right? We know the science. That's a really amazing thing about the stuff that's being done here at ESO. And I mean, science in general. We learn things by looking at other things, and then we create hypotheses, right? We think, I mean, Jupiter must be like this, like that. Pluto must be like this, like that, because we know from other examples in the universe. We created models, right? So that's science. And when we worked on this image together with the scientists, we were using, the knowledge we had from the science, and we imagine what it would look like, right? We get light from Pluto. From the light, we analyze the light. We can detect that it has methane. We know the temperature, so the methane should be frozen. So there's a lot of things we can imagine. And it's then when we send a spaceship there, and then we can actually prove, okay, some of our theories are right. And I was lucky that I worked on the image. But again, the credit is not mine. The credit is of the science we've been doing all throughout the years before.
Okay, so here we looked at two examples. One of exoplanet that we probably will never visit and see with our real eyes what it looks like, and another one, a dwarf planet, Pluto, where we actually could compare the artist impression with the real science image. And you have made a lot of other artist impressions as well, right? Can you just briefly mention one or two examples?
I mean, just to continue on the line of what we were saying, the very few examples where we can actually see the object a bit better after we made these images. I mean, another example is protoplanetary disks, which are places where stellar systems like our solar system are forming, and we used to do a few of these illustrations when needed. In the past, and then ALMA, this radio telescope, which observes a lot of these disks because they're like young objects, they emit in radio a lot. And nowadays we actually have really nice images of these disks information, and again they're also very close to what we used to represent. And again, the same principle. We know how this disk should look like. We know there must be gaps in the disk because we know if there are planets forming, they are accreting the matter around the star. So the science tells us how it should look like. And I think this is a very long answer to your question about how much of these images are real. And it's great to see that when we finally observe the objects a bit better, we have the confirmation that we're that we're actually close, and we're doing the best we can to represent these images as scientifically correct as we can.
Yeah. So let's zoom out a bit then, and we're going to start wrapping up this episode, but we're going to finish with talking about how these images then are perceived by the general public. And I'm going to start by framing this in around a topic that has become very current today, which is the question of AI. Today we see a flood of images produced artificially by AI. If AI is the correct term to use for that, I don't know. But there's a lot of images on the internet. There's a lot of fake images. There's a lot of images that give the wrong idea of what actually happens around space objects. So is there a risk that these scientifically based artist impressions kind of lose their value because they're sitting next to all of these other AI-generated images or fake images and so on?
I mean, I know it's a very important point and very important question and it's something that worries me quite a lot, not just in terms of the work I do and the science, but in general, I think for like society and humankind, the fact that we're producing these floods of images. I mean, I don't know if I have the answer, but it is true, because I don't think there's much we can do to fight that off, because the idea, again, these images, like we were saying before, is we want them to be eye candy because we want to captivate people's attention, but for a reason. We want to educate, we want to share knowledge. And it is true that, nowadays it seems like it's becoming easier and easier to create like fantastious images, space images using AI. It will create a sort of like, it will make people a little bit tired and immune maybe to these images. Maybe we need to rethink. I mean, it's very early on, as we all know. It's been happening in the past half a year, 1 year, that these very accessible software AI like Midjourney, DALL-E, for example, where people can just type a sentence and get a very colorful, beautiful image. But it will flood on the media, the internet. And I think it will create a sort of like a numbness to people when it comes to kind of catchy and interesting images. And it might make our jobs a bit harder because we need to penetrate that wall of noise of just colorful, beautiful, captivating images. And we want hours to go through because we want to share knowledge, and we have a goal, and not just to create a beautiful image for the sake of creating a beautiful image. We want to convey the sense of wonder, of magic, of the scale of the universe, and we don't want that to get lost in that sea of noise and images that can so easily be created. I don't know the answer. I mean, I'm just sharing your concern. I know there is something we need to kind of rethink a little bit. Because the idea, we always want to keep people interested in the science, right? Because that's, one of the ultimate goals of humans is to kind of continue, in our goal for more knowledge and understanding the universe and how it works. But also, there's a certain interest of self-preservation, right? Humans, they need to know more about the universe to also know our future here in our own planet. So that's the goal. To continue sharing that knowledge, but we need to find maybe new strategies because, our old techniques maybe might not be as useful in the future.
I definitely feel this risk of image fatigue because of the multiplication of images that we see today. But let me also touch on a topic that you raised here, that you say that besides, of course, communicating the science, an important point with these images are also to instill a sense of awe and feeling of beauty in front of the universe. But I got a very good question from a student once. I was giving a talk for a museum exhibition, which was about space, and one of the students asked me a question that I've been thinking about ever since. Because he said that, in astronomy, all these observations of black holes, colliding galaxies, gamma ray bursts, and so on, that are actually very deadly and dangerous objects, don't they instill a feeling of nihilism and like loss of meaning? And that's not what science communicators want to communicate, a sense of nihilism and loss of meaning. They want to communicate this feeling of awe and so on. And so this is a question of what kind of emotions do you want to communicate, and why awe and beauty? Like, why have we chosen those two emotions or aesthetics?
That's a very good question.
That came from the student. It was a philosophy student.
I think, for me at least, on a personal basis, I see it in a different way. I mean, I feel like there was always one of the things I liked a lot when I was when I started reading that book from Carl Sagan was, I mean, it put my personal life in perspective, right? I mean, it's one of the great things. It's a cliche. It's something that people say a lot about astronomy as well, is that it kind of grounds you, makes you feel, shows you the scale of your problems is so minuscule compared to, two black holes colliding and emitting a gravitational wave across the universe. So that really puts your life in perspective. I don't feel like this sense of nihilism. I feel it like I just appreciate life a little bit better by feeling like, our mundane problems are just that. They're mundane. They shouldn't take so much space in our head, because indeed it's a little bit meaningless. Yes, it is a bit nihilistic to think that way, but for me it makes my life better, because I feel better about the world where we live, because it is magical. It's fascinating that we, in this chaotic, mysterious universe, this place Earth came to be with the right conditions, that we came to become alive, and the two of us are here sitting. So that it makes me, this sense of wonder. So to say it in another way, I don't feel this nihilism, but I feel the sense of wonder. I feel like this is incredible, and I think that's what I feel when I work in a place like ESO all the time, or when I'm feeling down, when I'm feeling taken over by one of those minuscule problems, like, my refrigerator is broken, that kind of stuff. I just think, the kind of stuff that people are doing here at ESO, building the biggest telescopes in the world.
So when your refrigerator is not working, you look at your own images.
Exactly. Then I feel better about myself. No, it's just, again, it's like, we all do this, right? We all need to focus on our day-to-day. We need to do our jobs and get money to pay our rents, and that kind of boring stuff we all have to focus on, or most of us. But when you look at what the kind of stuff that people, the exciting people at ESO, the kind of work they're doing, the engineering, building these crazy, incredible machines in the most remote places in the world, driest, harsh conditions, and they're building machines to understand how the universe works. And of course, sometimes the images the image of the universe which is created is an image of chaos and randomness, but still, the solar systems are created in that chaos, and stars are born, and then planets are born, and then the right conditions for liquid water happen, and life appears, and I think it's fantastic. Yeah,
it's an amazing story, the story of how everything came to be.
Yes, yeah. And so, sometimes we get our refrigerators broken.
Yes,
and we need to fix them.
Well, it's still mysterious for me how the refrigerator works. Maybe more than
yes. You need to get a physicist and talk about entropy and whatnot.
Exactly, it's very, very complicated.
Another episode.
Yeah, another episode. So let's wrap it up. Final question then: if someone who has listened to this want to either see more of your or ESO's images, and maybe even get started with doing artist illustrations of space, or processing science data and producing images, where would you point them?
So ESO website, so ESO.org. We have a really extensive gallery with all the videos and all the animations and all the illustrations we produce. They're all Creative Commons, so people can use them freely. So that's something that's part of our mission, is also to give away everything we produce, so people can just grab them, use them, transform them, as long as they still credit ESO. We're happy about it. So that would be the number one place to go. So ESO.org. And naturally, if you have a taste for science and art, just start experimenting, fiddling, playing, and imagining new ways to represent, the mysteries of the universe. And then, maybe maybe you can find yourself doing a similar job to what I do.
Yeah, fantastic. Okay, thank you so much, Luis Calzada.
Thank you for inviting me. Pleasure to be here.
Thank you. Bye.